Hi, physics. Mr. Janowski here. This is problem 1 from the Chapter 13 study guide. So, in this problem, we have 3 bowling balls, each with a radius of 0.108 meters. I Googled it. They're sitting on the ball return rack at the bowling alley. We know the masses of each of the balls. And then in italics, it says, use the drawing above to figure out the distances between the centers of each ball. Yeah, drawing sketches, really helpful. Physics teachers love sketches. So let's see what we're actually trying to figure out here. So for part A, what is the gravitational attraction between the first and second ball? So, wrong tool. Give me a sec. Boop. So So what is the gravitational attraction between the first and second ball? So what we want is F sub big G 1, 2, seems like a good name for it, is equal to question mark. And what units do we expect this to have? It's the force due to gravity, so this will be in newtons. So this is for part A. And then for part B, F sub G between the first and the third ball. So F sub G 1, 3 is equal to question mark newtons. Now let's look at this, the thing in italics. Use the drawing above to figure out. All right, I can kind of draw a straight line-ish well enough. Okay. Use the drawing above to figure out the distances between the centers of each ball. So remember, we're dealing with bowling balls. Bowling balls are spheres. So one of the key ideas you need from this chapter is when you're dealing with spheres and their gravity, you need to measure from the center of each sphere. So what is the distance between the first ball and the second ball? Well, let's see. We have to measure the distance from here to here. So let's call this D12, the distance from the first one to the second one. And what is that distance? Well, notice if we measure straight across, we're going one radius from here to here, and then another radius from here to here. So a little r there, a little r there, which means D12 is equal to 2 radiuses. So 2 radiuses in this case, 2 times 0.108 is going to give us 0.216. So we've got that. And let's do the other part, the thing we need for part B right now. And then we'll get to the math. The math part should be easy if you can figure out the radiuses correctly. So when we're doing part B, we need to figure out the gravitational attraction between the first and the third ball. So we need to measure the distance between them from their centers. So we need to go from this point here to this point here. So what we want is this distance, D13. Looks a little sloppy, but it will do. So what is that distance going to be? Is it going to be 3 radiuses? No, it's not, because look, you have one radius from here to here, another radius from here to here, another radius from here to here, and then one more radius from here to here, which means D13 is actually equal to 4 of the radiuses of the bowling ball. So what is that distance going to be? 4 times 0.108 is going to give us 0.432. So good. So after that, this should just be basically plug and chug. So let's see, as long as we can figure out the right formula to use. So we've already done the hard part. So part A, we want to know F sub G 1 and 2. And what's our formula for F sub big G? It's going to be big G, first mass, so M1, times the second mass, which in this case will be M2, all of this over distance 1, 2 squared. So you just put in the numbers. 6.67 times 10 to the minus 11th with whatever the units are. Nobody cares at this point. There's just okay. The units are newtons meters squared per kilogram squared, but yeah, you don't write those out. It just takes too long. So even I get lazy on that one. And then we need mass one. Mass one is this number here, 3.64 kilograms. Sorry, that's a 4. It kind of looks like a 9, but that is a 4. Times mass 2. So what is mass 2? 5.46 kilograms. And all of this gets divided by D12 squared. So D12 is what we figured out above, 0.216 meters. And this gets squared. So if you do all that in the calculator and you get your order of operations correct, what do you get? You get 2.84 times 10 to the minus 8th, and the units will be newtons because it's a force due to gravity, so its units will be newtons. So put a box around it and think of this. Does this make sense? Well, the most outstanding thing about this number is that it's really, really tiny. This is something times 10 to the minus 8th newtons. So we're dealing with a hundredth of a millionth of a newton. So it's a really tiny number. Does that make sense? It does in this context. So even though bowling balls are heavy, and these bowling balls are as close to each other as they can be, you still get a very tiny force because gravity is so weak. Because our number for big G is something times 10 to the minus 11th. So yeah, the force due to gravity is very small. So when two bowling balls are sitting next to each other on the ball return rack at the bowling alley, there is a gravitational force between them, but it's super, super tiny. So yeah, you wouldn't notice it. So basically, yes, our answer for this makes sense. So we give it a check. On to part B. So for part B, we're looking for F sub G 13. So this is going to be equal to big G, first mass. And I'm going to write M3 because we're dealing with our other mass in this one is the third bowling ball. So why not call it M3? And this is going to get divided by D13 squared. So go to the numbers. And again, I'm a big believer in this step. One of the last things you should write when you're doing this problem is write down all of the numbers you're going to put in the calculator. Don't try to go straight from the formula to your final answer. Actually take this step, write down the numbers. So that's the mass of the first ball. The mass of the third ball is this one, 7.28 kilograms. And all of this gets divided by D13 squared. D13 is this number up here. Whoop. So 0.432 meters, and this number gets squared. So if you do all that, the number you get should be 9.47 times 10 to the minus 9th newtons. So put a box around it. And step, does this make sense? Well, notice this actually is a smaller number than we got for our answer for part A. So yeah, 9.47 is bigger than 2.84, but that's not how scientific notation works. Because our top number is times 10 to the minus 8th. Our other number, our number for our answer for part B, is 10 to the minus 9th, so it's an order of magnitude smaller. So we got a smaller force. Does that make sense? Well, let's think about it. So comparing part A to part B, well, both of them involve the first bowling ball, mass 1. The part A involves the second bowling ball, and part B involves the third bowling ball. And the third bowling ball is actually more massive than the second bowling ball, which might lead you to believe that the force of gravity between that one and the first one would be greater. But it's important to realize it's also further away. Didn't want that mark there. Yeah, this number here, 0.432 meters, is a bigger number than this. So the fact that 1 and 3 are further away than 1 and 2 are is what gives us a smaller force for that. So hopefully you can see that this answer makes sense. Again, it's a really tiny number. And the key, again, is, make a sketch, or in this case, use the sketch I gave you. Because if you can figure out what the distances are, hopefully it's clear now that you're looking at the sketch what the distances are, and you can remember that we're measuring from the center of spheres, then it should be a fairly easy problem. The stuff at the bottom, that's all plug and chug. So yeah, if you could figure out how to use the sketch correctly, hopefully it wasn't too bad. So hopefully you found that helpful.